Wonderful.
Great.
We are delighted to have Dr. Jack Holguin here to tell us about collinear factorization. Dr. Jack is an early career fellow funded by the Leverhulme, I'm guessing,
Never
Trust.
Hume.
Okay.
Yeah.
Apologies. At the University of Manchester. Previously, Dr. Jack was a postdoctoral researcher at the École Polytechnique in Paris, ooh la la, after completing their PhD at the University of Manchester. Jack works on a range of topics related to quantum thermodynamics, contributing to studies on QCD factorization, the development of the Holguin event generator, and the application of jet substructure to heavy ion physics. We're really excited to hear about this. Thank you so much for taking the time. Please take it away when you're ready.
Thank you, and thanks for the invitation. So yeah, I'm going to talk about what is collinear factorization, and I've tried to set this up as a preliminaries to my talk next week, where I'll be discussing how does collinear factorization break. And so this talk is going to try and give a very physical picture of the factorization that it was developed by Colin, Soper, and Sterman before next week, where I talk about how that picture can be complicated. So this is big picture. The goal of the talk is to understand this formula and what all the ingredients mean. This is sometimes referred to as the master formula for processes at hadron colliders. And I'm going to do this at 3 levels. I'm going to do it pictorially first. Then I'm going to talk about some fixed order matrix element calculations. And then I'm going to try and link that into a perspective from sort of resummation and what the factorization is really saying. We'll see how far I get. I've got a lot of slides, and I'm very open to questions as I go along. Okay, so starting from the big picture, the process we're wanting to consider is something like at the LHC, where we've got 2 protons colliding, so proton A here and proton B, and they're at very high energies, so that the collision, instead of being thought of as proton scattering, can be thought of as the constituent particles inside the proton scattering, so the quarks or gluons. And these undergo what's known as a partonic collision. So the way I'm going to draw all of this is I use blue for the protons, which is the initial state. I'm using black for the hard particles, hard meaning very high energy, that were produced in the initial collision of the quarks or gluons. And then green is the extra radiation that comes off from that collision. So that is higher order corrections, more gluons being radiated, all that sort of thing. All right, let's go turn by turn through this formula. So the first thing here is the parton distribution functions, or PDFs. And these describe very physically the probability of finding a parton, which is a quark or a gluon, inside the proton with a given fraction of that proton's momentum, which here is given by, let's say, if we focus on the left-hand side, where we've got proton capital A, becomes parton little a, which could be, like I say, a quark or a gluon. It's got a fraction xa of the total proton's momentum. Okay. And what this formula is telling us is we compute the scattering of this process, the cross-section for the scattering, by convoluting these parton distributions against a partonic cross-section, which is the cross-section for the quarks or the gluons to scatter. This is at a center of mass, which is therefore at xa times xb times s, because it's lower than the overall proton center of mass, because these quarks and gluons only have a fraction of the proton momentum. And then continuing through this formula, the really important thing about it is that the claim is we can use this for any observable we're particularly interested in, with some caveats. So when we do a measurement at the Large Hadron Collider, we'll have cuts on the final state we detect. We might require, for instance, that we see at least 2 jets with a given amount of transverse momentum. Maybe we have cones around the beam directions, which are vetoed because we don't want to look at things down the beam axes. And that's all encoded in this formula into what I've called V. V is the observable or experimental cuts. And I've given an example in the diagram of what that might look like, drawing cones around different axes where we're collecting radiation. Okay, so now what's this mu in the partonic cross-section? I'm not going to talk about that particularly in this talk, but that's the renormalization scale of the overall process. And that's because when you add loops into the whole calculation, you get divergences and they need renormalizing, and they result in things such as the strong coupling will run with the scale. But this won't be a focus of the talk. The main focus is what are these mu f's? And so these mu f's are what's colloquially known as the factorisation scale. And a very intuitive picture of what they're giving you is they're saying what we consider to be part of the proton versus what we consider to be part of the partonic scattering. So looking at this diagram, I've drawn two extra gluons in a sort of dark purple. For one on the left-hand side here, actually, just 1 second, I'm going to stop sharing my full screen to see if I can find a way to get a laser pointer-like thing so I can actually point at things on Keynote. I don't know how to do this in Zoom. Can you see that? No.
No.
Okay, well, I'll have to leave it and just say what I'm talking about. Okay, so the gluon on the left-hand side here, that's the I've written it has a transverse momentum less than the factorisation scale, whereas the gluon on the right-hand side, I've drawn it to within our partonic process, the dashed lines either side of mu f, and that has a transverse momentum higher than the factorisation scale. And so this factorisation scale is basically saying that very low transverse momentum particles we consider to be a part of the proton structure, whereas very high transverse momentum particles relative to the scale we're considering to be a part of the partonic cross section. Now, the end cross section you can see on the left-hand side of the formula doesn't depend on mu f, and so mu f should actually be cancelling in the end. But for any practical calculation where we approximate the partonic cross section at a given order in perturbation theory, the mu f dependence will remain, and so it's a choice that we want to optimize. Now, the natural choice is to let mu f be quite close to the partonic hard scattering center of mass. And what this then gives you the intuition of is any particles which have a transverse momentum larger than mu f, then they have a transverse momentum that's comparable to the hard process we're scattering. And so it makes sense that you consider it as a part of that process. And anything with a transverse momentum less than that, we're considering to be part of the structure of the proton. Now, this actually, I think, is more intuitively if you think about it in position space. So transverse momentum in position space is therefore talking instead about the transverse separations between things, transverse wavelengths that are being probed. And high transverse momentum is probing very short scales, short distances. And so we have a very high energy collision, and mu f being set near that collision center of mass is saying that high energy collision is only probing transverse distances across the wavelength of order the transverse size of the collision. Everything else is sort of a background of what's going on in the proton that isn't directly involved in the collision. And so we consider that to be a part of the proton structure. And in going back to momentum space, that means that stuff is things with a kT less than mu f. Okay, so that's a very physical picture for what's going on. Does anyone have any questions about that before I move into doing it a bit more mathematically? If not, I'll proceed. And the main thing to highlight is that the object of discussion here is the collinear limit of radiation from the initial state. We're talking about gluons being and quarks being emitted from the proton and their transverse momentum relative to the beamline. And we're asking questions about whether or not their transverse momentum is much less than the center of mass of the partonic collision. So they're relatively small transverse momentum going down the beamline. And so with this said, the important thing to consider is the limit of the collinear limit of QCD radiation. And so let's consider the simplest possible Feynman diagram which contains this collinear limit and start building up the picture from there. So let's consider this Feynman diagram where I simply have a quark that fragments into another quark and a gluon. And we want to expand in the limit that the gluon is emitted at a low transverse momentum, so the KT of the gluon as I've labeled it here. The natural variables to do this are, so the quark after the emission, I've given momentum Q. And it now, after the radiation, will have a fraction of its initial longitudinal momentum, which that fraction is given by Z, plus some transverse momentum due to the fact it's recoiled off the gluon that it's radiated. And then the gluon here has momentum K, and it has the rest of the longitudinal momentum of the initial quark, and then the opposite transverse momentum. So the two terms sum together to give you back the momentum you started with, which is P. Now, if you calculate this diagram and expand for small transverse momentum, you get the squared matrix element I've given here. Doing this calculation is a little fiddly. You need to make sure that all your polarization vectors of the outgoing particles are properly on shell. And that can be a bit of a faff, so I've not gone through it in detail here. But it's a textbook result. If you wanted to see, for instance, a calculation of it done, you could look at chapter 5 of QCD and collider physics by Ellis, Sterling, and Weber. Okay, now continuing on with this calculation, we also need to consider how we're going to integrate over the phase space of the final particles, because if we're going to measure anything, we need to integrate the particles that are produced over the space which we're measuring. And this means decomposing the Lorentz invariant phase spaces for Q and K, I've written out here on the left-hand side, in terms of the variables of Z and KT. And that can be done on, again, to leading order and KT on the right-hand side. And if we put this all together, what we get is the following. So let's embed this calculation I've just described inside a physical process. So the quark has come from a proton. This is needed because otherwise the diagram wouldn't be gauge invariant on its own. But because a proton is color neutral, this now is a gauge invariant Feynman diagram. And in doing so, we get the matrix element we had before, this m squared, times by the phase space for the particles, times by this f on the left-hand side, which is the parton distribution function for the proton. In other words, the probability to have found this quark in the proton. And then this 1 over p squared, which is the propagator momentum for the quark, because we've now embedded it as an internal leg. And if you substitute in all the results from the previous slides and simplify it down, you get the answer on the right-hand side here. Now let's look at this closely. And there's two potentially worrying properties here. It is singular when KT goes to 0. So when the quark is the emitted gluon is perfectly collinear to its parent quark. And it's also singular when the energy of the gluon goes to 0, because that's equivalent to Z equals 1. So that's something that we'll have to address what the consequences of in a few slides' time. But first, let's just recognize what this is. This is what's known as the collinear splitting function and is often written as P. And it's completely universal, this turns out. You could be doing this for any process. So here we have a quark emitting a gluon, but you could have a gluon emitting a gluon or a gluon decaying into two quarks. And it turns out it's always possible to write that matrix element as the cross-section for the process with the collinear particle is equal to the cross-section without it times by this splitting function, and then the same phase space factor that we derived on the previous slides. Okay, So how does this look diagrammatically? Get some intuition back again. What I just said is what's on this left-hand side. So we've got a general process with an arbitrary number of particles involved. And one of those particles we've labeled as A, and the other one we've labeled as B. If we calculate the squared matrix element for that, that's the cross section, and take the limit that B goes collinear to A, it will always factorize into the squared matrix element as if B wasn't even present, times by this probability for A to emit B in the collinear limit, which is given by this splitting function P. And quite amazingly, you get the exact same result if you also considered a loop, just with a minus sign relative to the previous one. A loop on particle A can be factorized as the process without that loop times by a splitting function describing the loop momentum. And this is a consequence of something known as the KLM theorem for anyone who's doing this in more detail. I don't know if you've got modules on QFT which might discuss the KLM theorem. Okay, so that's the preliminary matrix elements that are involved in collinear radiation. But, yes?
Go back to the previous slide. Why is the squiggly equal to sign?
Squiggly equal to is I'm throwing out all the higher order corrections in KT. This is in the collinear limit. So where the emission, the momentum running around the loop is collinear to the parent particle. There are corrections to this proportional to KT and then KT cubed and so forth and so forth.
Okay, thank you.
But just to really emphasize why we're doing this, I highlighted before there is a collinear divergence here, right? If KT goes to 0, your measure, phase-space measure is dKT over KT. So that diverges logarithmically. Any corrections to this won't diverge anymore. So our calculation of this process is basically a divergent piece plus finite stuff. And it's a pretty good approximation to say in the limit that one piece is going to infinity and the rest are finite, I can just keep the infinity piece. Okay, so now let's consider actually putting this into a computation of an observable. And the reason I'm doing this is if we go back to the formula I said we want to describe this master formula, it's talking about separating out the collinear gluons from the initial state from a partonic process in the presence of an observable that we're measuring. And so we need to know what these observables do. And let's do a little test case. The simplest observable we could probably consider is, let's consider an E plus E minus collision, and it produces 2 jets, which is what I've drawn here. So we've got an electron and a positron come in, they annihilate to produce a quark and an antiquark, and then those quarks and antiquark will both radiate more gluons, which are in green here. I'm thinking E plus E minus because this means we don't need to include the PDFs I previously wrote down, so it's going to simplify the calculation. We'll put everything back into the full context a bit later on. And let's think of the simplest observable we could consider, which is, for instance, something like we draw a cone around the jets and we veto any events with too much radiation outside of that cone, and the cone diameter is tau. The Lorentz covariant definition for doing this is something like I've written down at the bottom here. So we're requiring that any event we're interested in has tau less than or equal to, well, has the following equation less than or equal to some fixed value of tau. And this equation is, so N1 is the direction of jet 1, N2 is the direction of jet 2. So the dot product of M1 and a particle momentum P, well, P is one of the momentums in an event, is therefore obviously very small if it's going down the jet direction and very large if it's going orthogonal to it. To be clear, these are for 4 momenta, not the 3 momenta. And so, yeah, we're requiring that this is always less than some value of tau, which is our cut on the event. I'm using this definition because actually this is what's known as the 2-jettiness. And the observable I'm going to be considering next week when we talk about collinear factorization breaking will be the jettiness. So it's going to be next week's discussion will be a more complicated calculation of this similar process. Right, so what this looks like. We have two terms in our calculation. Let's first look at the one on the right. So we're doing this at a fixed order. So at fixed order, we've produced a quark and an anti-quark, and we're going to compute the first alpha S correction to that. So there's two options. We could have a loop, or we could emit another gluon. The loop is very simple, and that's what's on the right-hand side here of this formula. And in the loop's case, there's no veto whatsoever, because the jet axes will lie along the axes of the direction of the quark and the anti-quark. And so if we compute this formula on the bottom of the screen here with the momenta, you will always get 0. So it's always less than any value of tau. So the loop we just integrate over completely is untouched. However, on the term on the left here, the first term, this is where we've had the quark or the anti-quark has radiated a gluon. And the boundary of the cone that we've drawn causes that gluon to either be accepted or vetoed, depending on how perpendicular it is to the jet direction. And then the matrix elements are determined by these splitting functions that we just derived, because we're going to do this we're just keeping the collinear limit of the gluon and the quark. The gluon that was emitted out of the loop. And so this observable now enters just as a modification to the phase space boundaries of the emitted gluon, which, if you look on the left-hand side, is simply sitting as this V in the upper limit on the KT. The KT can normally run all the way up to the center of mass energy divided by 2. That's just by momentum conservation. Now it has to stay smaller than some smaller value so that it stays inside the cone. All right, so we do these integrals, and what do we get out? Well, we get the following result. The first term here on the left, this is the tree level result. I didn't write this on the previous slide. The sigma with a 1 above it means I'm doing the alpha S correction. This first term is the no emissions term, this sigma 0. And then we have to add to this alpha S correction, this sigma 1 we just computed. And that all collapses down to what's on the right-hand side, which is sigma 0 times by 1 minus the solution to those integrals. And there are 3 terms to the solution to those integrals. There is a term which goes as log squared times by the observable cut V. Sorry, I've started using V here. That's a mistake. I'm calling it tau here. It was V in the master formula. Tau is equal to V. Apologies for any confusion. I did say there would be some typos to be found, and that's the first one.
Sorry again, Jack. Yeah. So the n is over there. What do they mean? Like so you dotting n with the momentum.
Sorry, so say that again, please.
You just go back to the formula again for where you two jettiness. And then the left, yeah. So it's the minimum. So what? Tau is greater than the minimum of, and then in the brackets you have what?
So the minimum is N1 is the direction of the first jet, and N2 is the direction of the second jet. So at fixed order, N1 is the direction of the quark, say, and N2 is the direction of the anti-quark. And by direction, I mean it's a light vector pointing in that direction. So it'll be something like, let's say the quark is going along the y-axis. It will be 1, 0, 1, 0. And then P are the momenta of all the particles that are produced in the collision. So if you think about a gluon that's close to the quark, then N1.P is always going to be smaller than N2.P, which is going in the opposite direction. And so this minimum is just basically providing a cut on the sum of all the momentum dot producted with the direction that the quark is going in. So that's what this requirement that tau is greater than some value. in terms of these momentum. Does that make sense?
Yeah, cool, thank you.
It's important in this that the ends are like.
Okay, good.
Yeah, the ends are like vectors that point in the direction of the quark. So at first order, N1 will just be the momentum of the quark divided by its energy. The form momentum of the quark divided by its energy. Okay. So we did those integrals and we get this result. We have a tree level result plus a correction, and the correction is negative. And the correction also is actually completely finite. The divergences I previously pointed out that were present in both the splitting function for the emission and also for the loop diagram have summed together and cancelled. But what they've left behind is a logarithm. Well, they've left behind actually two logarithms. They've left behind a logarithm of the observable squared plus a single logarithm and then some constant remainders. And now what's the problem here? The problem is that these logarithms are actually very large. If we wanted to use this observable to tag on that there were two jets in the event, we need that our cone around the jets to be quite small. So this tau value could be, say, 0.1, could be 0.001 in the process we're interested in. So the logarithm could be a factor of 10. And then if you have alpha s times by something that's around 10, that's just an order 1 quantity now. And so it looks like our perturbative correction is actually just as large as the zeroth order term. And that's clearly a problem. And this continues to higher and higher orders. If we did this at 2 loops, we would find a term which goes as alpha squared, but times by log to the power 4. And again, you'd find that means the 2-loop result is just as important as the 1-loop result, which is just as important as the tree-level result. The general statement is what I've written at the bottom here, which is that as you go to alpha to the n, you will always find a log to the power of 2n for this observable. And so every term in the perturbation series is just as important as the previous one. And that's quite worrying. And what it tells us is you can't treat this at a fixed order. You need to be resumming these logs. You need to sum the entire series of the perturbation series back up again. Okay, so how do we do this? This is going to be the crux of what the master formula is doing for us. Well, very typically, the easiest way to do a resummation is to set up some sort of evolution equation in the observable or flow equation. This is often achieved by renormalization group. One person before the talk asked me if I would mention Sket at all. This is what Sket does for you, and that's about as far as I'll say on that topic. And you could, but here's a very simple example of how this could work. So what we've just computed is this observable at fixed order, where we found sigma is equal to this sigma naught minus the logarithms. If we differentiate with respect to the observable, we get this equation I've written here. That's just differentiating the previous slide, where I've recognized that sigma, capital sigma to the 0 is equal to the Born cross section little sigma. Now you can postulate that this will extend to all orders, and in fact you can prove this. That would mean that we can remove the perturbative superscripts, sorry, for the alpha s in the expansion that we're computing, to get the following equation here, which looks exactly the same but no superscripts, which we can now solve, and you find that this observable is actually equal to the exponential of minus the logarithm that we found. So what this means is that we look like at fixed order, we had a process which we know has to be positive definite. It's an observable, it's a cross section, but our calculation is equal to a sigma naught minus something that can become arbitrarily large as we tighten our cut. In other words, the cross-section could have become negative. We do the resummation, and what this is actually telling us is the cross-section never became negative. The cross-section was diving to zero exponentially fast. And that's hopefully quite intuitive for the specific observable we're considering, because this observable is a cut on the amount of radiation we see. And if we cut so tightly that we don't see anything, obviously the cross-section has to go to zero. And that's exactly what this resummation has told us, that the cross-section goes to zero.
Can I ask,
Yes.
you mentioned that you had this like 1 minus loop stuff. Is the negative result coming from the minus loop stuff?
Yeah, so the initial calculation looked like this, right? We had the left term here was the emission, and the right-hand side term is the loop. Now, if you think about it, the right-hand side term has no cuts in it, so the loop is integrated over the entire phase space that the loop could fill. But the left term has a cut on it, which means that the emitted particle can't go too far away from the jet axes, because then we'd have vetoed the event. And that means that the term from the emission is always smaller than the term from the loop, which is negative. So when we add the two together, we get 1 minus this logarithm.
I see. Thank you.
And this is basically telling us that the presence of this log is because it's the residual of the divergence we've cancelled. But it's telling us that actually we have to resum our perturbative series, because otherwise we could have a negative cross-section. Okay, so this is what that looks like in this particular observable. Let's now go on to the case of interest to us. We're talking, which is a bit more complicated. We're talking about the evolution of the protons and factorizing that from a cross-section. And I've just argued, to make anything physical, we need to sum the splitting function contribution for an emission with the one from the loop. And we need to do this so that we formulate a resummation of the observable. In this case, that resummation is for the parton distribution function, which we can now talk through. Fortunately, we've already done all the calculations we need to do this calculation in this talk, because it all just depends on these splitting functions. And our goal now will be to recast that calculation we've already done as a flow equation that we can solve, just like a differential equation on this side, just like we did with the observable. Okay, so to start this, let's make a more complete picture and really specify what is it we're observing from a proton when we do a collision. We have a proton coming in, and from that proton, a quark with momentum x primed times the initial proton momentum could be pulled out, x prime being its momentum fraction that I said about before. Now, this quark could radiate a load of gluons, which take away some of that momentum, so that what we eventually measure is a quark going into the hard scattering process that has momentum x times the initial proton momentum plus some transverse momentum. Okay, so we're measuring the blue blob in this diagram, and what we're getting from the proton originally is higher up in the chain. It's the quark with momentum x prime times p. So we're going to have to track, say we started with probability to find x prime times p, we're going to have to track how that probability changes because of the quark has radiated a load of gluons. And it's easiest done if we plot a diagram for this, for the variables of the quark. So the quark starts in the proton with no transverse momentum, at least in this picture. So on the x-axis of this plot, so at x equals 0 on this plot. But it has some fraction of the proton momentum which is the value of the y on this plot. And as it progresses towards our hard process, where it's going to scatter towards our measurement, it's going to take some path through this plane. And our measurement I've drawn on here is the blue box. That's where we are specifying in our measurement that we have seen a quark with a momentum fraction x and some transverse momentum kt. And so we want to write this now as a flow equation. We want to look at all the possible paths a quark could have taken through this plane such that they ended up in our box. And we write this as the change in the parton distribution function, which is now the probability to find a quark with a momentum fraction x and at a transverse momentum resolution of kt, is equal to the amount that flow into this box minus the amount that flows out of this box. Okay, so this is a little abstract, but fortunately we've already done all the work to compute these two quantities, because let's just imagine what causes you to go down on the plane. Well, that means you've lost some of your energy. The quark has lost its energy, so it must have radiated a gluon. So every step down is a quark losing some energy by radiating. Every horizontal step is the virtuality of the quark being reshuffled, its transverse momentum being reshuffled with the process. So that's like loops connecting it to other things. Now, let's add up all contributions, and the bottom results are here on this slide. But the key thing to note is that if you did this very carefully, everything flowing in from the left-hand side of the box cancels with whatever flows out from the right-hand side, because they both have the same probability. They're both given by the probability of a loop, which does not change the properties of the quark. But flowing in from the top does not equal flowing out from the bottom. Flowing in from the top means we start with some parton distribution function of a higher x value and goes in, whereas flowing out the bottom means we start with a lower x value that started inside the box and then flows out. And so the two terms that matter are these here. Going through the flowing in term, this delta log kt, that's the width of the box we're measuring. It's a log kt because we have this kt divergence, so it's delta kt over kt. And then the splitting function, the matrix element for the quarks who have been emitted, times by the PDF to have seen the quark in the first place. And importantly, the argument of this PDF is x divided by z, because it came from a particle which had a higher momentum fraction of the proton, and that momentum fraction is equal to the current momentum fraction of the quark that you see divided by the momentum fraction that it lost. Now the out term has the same basic structure, other than that the PDF enters differently, because it's the PDF now from inside the box and flowing out. So instead of being x divided by z, it's just x. Okay, so we add all these terms together and we get and turn it into a differential equation, and we get a very famous equation which is known as the Dirichlet equation for the evolution of a PDF. So this describes, as a differential equation, how the probability to find a particle inside the proton, a quark or a gluon, here I've divided it for a quark, changes as a function of its momentum fraction x and the scale kt that we're resolving it. And it's given by these splitting functions on the right-hand side. As you can see, this is a non-linear equation. It's quite unpleasant, so it can't be solved analytically. It has to be done numerically. But still, it pins down what's going on. But an important point to highlight is that previously, I said these splitting functions give us two divergences when kt goes to 0 or z goes to 1. In other words, when the emitted gluon becomes collinear to the parent quark, or when the emitted gluon has 0 energy. If you look at this equation and you imagine setting z equal to 1, Once Z is equal to 1, those two PDFs are equal to each other. And the whole equation vanishes. It becomes equal to 0. And so there is no soft divergence anymore. There's only a collinear one. There's only the log KT in the differential equation still that could potentially diverge. Okay, so this resums logs of the transverse momentum that we're seeing, but it doesn't care about any soft gluons being emitted, any low energy gluons being emitted. Let's put this back into the overall formula and ask what does this tell us, and consider the jettiness observable I previously discussed. Well, we know inside the partonic cross-section, this sigma hat, there are log squareds. There are these Sudakov logs that, if we calculate them, they become this exponential of minus log squared of the cut of the jettiness. But pulling the PDFs out is telling us that the logarithms coming from the initial state radiation, all the gluons coming below μf, are single logarithms. They only depend on alpha s times log of μf or log of the KT. So this is actually telling us something very important. We previously, without any knowledge of this master formula, we might worry that the protons would also see a log squared, or the whole thing would be really complicated and everything's mixed together. This formula is telling us that these log squared terms, which are known as Sudakov logs, only exist in stuff that's sensitive to the final state, and the protons obey a very simple single log evolution in the KT. So practically what this looks like in terms of diagrams is it telling us the following is true. We have this general process going on, and there is, on the left-hand side, there is a violet gluon I've drawn on, which is an emission that's collinear to the beam axes of the protons. And the master formula is telling us that we can compute this observable and resum all the logarithms by reattaching this red gluon, which is linking the initial state to the final state. And therefore, because it's dependent on the final state, it will have a Sudakov logarithm, one of these log squareds. We could reattach it to after the violet gluon so that we can imagine the red is just a part of the partonic cross-section and the violet is a part of the proton. Here's that worked out a little bit more precisely. So these red ones, on the left-hand side, I've drawn now the sort of worrying situation to all orders. So not all orders, but like a high order. So there's loads of gluons going around. And these red gluons are all problematic. They're all attached all over the place. And if we did have to compute this entire matrix element, our life would be very difficult. But the master form is telling us we can rewrite it in the middle form, where we've attached the vertices of the red gluons to going after all this collinear radiation, and therefore we can pull the collinear radiation into the initial state. Okay. Now, the key fact that lets us do this in the master formula is that the soft gluons, these red ones, actually only see the overall direction of the parent particle and its overall charge. Now, at this point, I'm just going to ask, it's 1:45. How much longer do I have before we want to have questions?
We love all the time and interest that you are, not interest, all the time you're willing to give us. You've put this together, so I think we're here
Okay,
until
brilliant.
You give up.
Brilliant. Okay. Didn't know if you had a hard cutoff at 3 o'clock your time. Okay. So let's look at how this can be achieved, and I'm just going to give an example of how you can do this rewiring of the red gluon at fixed order. But to do this, I'm going to have to give you a bit of machinery for handling color factors. That's also going to be crucial for my talk next week. So let's think about this first diagram here. The matrix element for this quark, which has a color index J, and then is propagating along and emits a gluon with a joint index A, and then that rotates the quark into having a color index I, can be written in the form that I've got on over here on the left. So the matrix element depends on A and I in the outgoing state. And this could be equivalently written as we pull out the Gell-Mann matrix, which is the vertex for emission of the gluon, which is then multiplied with the matrix element for just the propagation of a quark's color with the index J. And you can do this for any process. You can always pull out the Gell-Mann matrix for the vertex of an emission that's on one of the final state legs. So I've written a more complicated one down underneath. Here we have a matrix element which depends on a huge number of fundamental color indices and adjoint indices. I always will use I and J for the fundamental and A for the adjoint. And this is equivalent for the diagram I've drawn. You will be able to pull out this Gell-Mann matrix for the emission of this gluon A from the whole matrix element. But there's a lot of indices here and it's clearly a bit of a mess. Now, if we're going to go back to talking about these sorts of diagrams over on this slide where there's colors, where there's gluons attached all over the place, you can only imagine the amount of indices that are going to be floating around in Gell-Mann matrices all over the place for reattaching these lines. We need a bit of better notation and machinery to help us do this. And so the easiest trick to do this is to remove the indices altogether and think slightly more abstractly. So let's think of this matrix element with all these color indices to produce a gluon plus anything else, that's X in here, as a projection of an abstract matrix element, which is now some abstract tensor in a color space, projected onto a set of colors, onto those particular indices. So this is no different to project, you think of an abstract vector, and then you could project out its X component. Here we've got an abstract multi-dimensional SUN tensor, and we're projecting out the components onto particular color indices. Okay, so now how does this look if we do this in the case where I've pulled out one of these Gell-Mann matrices, like I said on the previous slide? Well, we can do the same thing if we introduce this bold P with a superscript A here, which is going to be a SUN operator, which projects onto a Gell-Mann matrix when you put it in a given color basis. And we give it a subscript based on the color line that it's attached to, the particle that it's attached to, so you know in which space it's acting. So for instance, let's say the emission came off the nth particle. The Gell-Mann matrix should be attached to the fundamental indices that come from running off the nth particle. And this expression on the left-hand side here at the bottom, you know, that would be a nightmare to work with if we had to see that all the time. But we can just keep track of that by thinking about this is the operator which generates a Gell-Mann matrix, sort of abstractly from the nth line, projected onto a given basis of color indices. Now, why does this help? Well, we always sum over the final state colors because we need to, everything we measure is gauge invariant. We can't measure a particular set of color indices. And so if we consider computing a squared matrix element, that reduces to the relation I've got here on the first equation, where the sum now over all the possible color indices actually is just an identity. And so we just have the overlap of these two abstract ends next to each other. This gives us a lot of useful algebraic manipulations now, which otherwise weren't transparent. For instance, in QED, we have charge conservation. And charge conservation tells us we have something electrically neutral coming in, and it decays. The sum of all the charges going out must be electrically neutral. In QCD, that is not at all transparently obvious when you are dealing with Gell-Mann matrices and structure constants and things like that. But we can now introduce that notation very easily using this more abstract notation, because if we consider a matrix element M and do a general gauge rotation on it in terms of this abstract notation, which is just this e to the I alpha A, where alpha is just some parameter, which we contract with a sum over all these possible all these possible color charges. So that sum over all of them is over all the possible particles in the event. So we're basically, every particle has an associated field, and this is doing a gauge rotation on that particular field. That therefore must equal the matrix element as if the gauge rotation hasn't happened, because matrix elements are gauge invariant. And if we expand now for small fixed alpha, we therefore find that it must be the case that the sum over all these abstracted color charge operators acting on the gate on a matrix element equals 0. And this is now much like the charge conservation in QED, because a gauge invariant matrix element is necessarily a color singlet, so it's overall color neutral. And so, and the sum over all color charges acting on it, it gives you 0 because it's color neutral. So this is a very powerful little relation. Right, with this notation, we can now write down a general form for one of these soft gluons. So one of those red gluons being emitted from any particle in the event. And it takes the following form. So we have a gluon that's emitted from X other particles, and it's equal to the matrix element for those X other particles, contracted in between it with 2 of these color charge operators. That's 1 for each vertex, because there'll be 2, because obviously it will be attached somewhere and attached somewhere else. And I and J are the lines of the particles that it's attached to. And then a kinematic factor omega, and we're summing over all I and J. And this kinematic factor only depends on the direction of the particles which it's attached to. It doesn't depend on those particles' overall energy or momentum. Okay.
Sorry.
Yes.
You have this extra like alpha superscript floating around. Is that that's not being summed over as well, right? Alpha.
Oh, so A you mean here? Sorry.
A. So yeah, A. Yeah.
Yeah. A is the adjoint index of the emitted gluon. As you can see here, so that's this on all the Gell-Mann matrices. It's a superscript A, and I've made that explicit so that the dimensionality of the tensor of M is the same before and after the emission, because otherwise you emit a gluon, you get, that's actually increasing the dimension of the color space if I didn't write the A explicitly. And yes, it is implicitly summed over. It's summing over all the possible color charges that the gluon could have in as an adjoint index. So it sums from 1 to 8. Of the 8 possible gluon colors.
Yeah, I was just getting confused because there was like the sigma notation for the I and J, and so I wasn't sure if you were also doing it for the A's.
Yeah. Sorry, implicit summation notation on the color indices.
Okay.
Same with on the on like the left-hand side relations here is implicitly summed over J1 and Jn.
Okay, thanks.
Okay, and yep.
So if we're imagining that this initial state mx, that we then sort of add this gluon emission onto, it's, I can imagine the next step is that we're gonna sort of do this iteratively. So if the state mx is already built up from, say, a gluon emission on some mx minus 1 state, do we need to worry about the order in which we pull out these Gell-Mann matrices?
Yes, you totally do. So what I'm going to do shortly is once we've got everything laid out, I'll do this for 2 particles so that we can see collinear factorization. And then I am just going to say that you can do this iteratively to get it to all orders. And you do completely need to worry about the ordering of the gamma matrices. You also need to worry about the routing of the momenta through the propagators that generate this omega factor if you're going to do it for multiple emissions. And really the proper way to do things at that point is to do what's in the Colin, Soper and Sterman proofs of factorization. Then you really put everything into what's known as a Wilson line. I'm not going to do that here. My goal is just to show you a single alpha S squared calculation of how things will drop out, so that you've got all the hopefully your foundations you need for when next week I talk about an alpha S to the 4 calculation where everything will break.
Okay, thank you.
But yeah, so the fact we can write a extra soft gluon attaching between 2 legs I and J in this form is what's known as the soft theorem, and it's a very fundamental part of gauge theories. But I'm not going to go into that in detail. Really, the fact we can write it in this form is all we need now to just proceed diagrammatically with showing that we can do the rewiring of the vertices that I was saying about. Okay, and so here is the argument. So the problematic diagrams are these 2 on the left, where I've got a gluon that's in red, that's going either before my collinear emission, that's in blue, or is attached to my collinear emission, that's in blue. Both of these are stopping it from being pulled away from the partonic process and brought into the PDF. And to keep the diagram simple, instead of drawing the full partonic process, I've just cut it off and put this vertical dashed line. And I've indexed the partonic process as J, say, so J is a particle in the partonic process. The emitted collinear gluon I've indexed as particle 2, and the quark which radiated it is particle 1 after the emission, or particle 1 plus 2 before the emission. Okay, so I hope that's clear. Now, obviously we have to coherently sum these 2 diagrams to get our cross section for the process. And in doing so, the important thing is that the soft gluon only cares about the directions of the people that emitted it, as I mentioned before. And so it's going to be attached to some of the particle J in the partonic process. And then it's going to be attached to either 1 or 2. But because 2 is collinear to 1, they both share the same direction. So the kinematic factor on this previous slide, this omega Nij, in both cases is actually just omega N1 Nj, and then the momentum Q of the soft emission. So that kinematic factor is always the same. So now what's the color charges multiplying it? Well, you'll get a color charge for the jth particle in the partonic process. That's what this bold TAJ is. And then you'll get the sum of the 2 color charges of these 2 diagrams. And then that will give you the full matrix element now for radiating this red gluon. And crucially, this sum is equal to the color charge of the T1 particle. So minus the color charge of the T2 particle. And there's a minus sign because one's in the initial state and one's in the final state. Now, if we use color conservation on the T12 particle, that means it's equal to the sum of all other color charges in the event without color T12 particle. That's using this identity I've got here in this slide. The sum of all color charges is equal to 0. And so we can write one color charge as equal to minus the sum of every other color charge. And if we do that, you actually find you can use color conservation and the whole thing becomes equal to because T2 cancels from the sum over everything, it's equal to the sum over all the color charges just without particle 1 in it, which is equal to the color charge of particle 1. So I've got a minus sign error here. There should be a minus sign in the in-between line there. And so what we get is the kinematic factor is equal to the kinematic factor we would have found if the red gluon was attached to particle 1. And the color charge is equal to the color charge we would have got if it was attached to particle 1. So we can just move it along and reattach it. And so this sum of these two diagrams is equal to the diagram with the gluon reattached. Now, if you iterate this over and over and over for an arbitrarily large number of gluons, that does indeed let you pull out this collinear gluon from the red one. But an important step in this process is that the kinematic factor here, this omega, that is the same for each of these different diagrams. And so what's going to be very important is that whatever measurement we make doesn't end up integrating this kinematic factor differently between these two diagrams. If it does, it ends up, that might break our ability to factorize these two things apart. So the precise statement really is that we can use this formula, provided our measurement is sufficiently inclusive, that we can still do this algebra that I just described, where we can pull the collinear gluon out from the soft gluon. Okay, so generalizing this to any number of emissions does indeed show that you can factorize the Sudakov logs, which would come from these red gluons, from the Dirichlet logs, leading to this master formula. But it's delicate. As I said, we need the color charges to add up correctly, and that depended on the factor, on the kinematic factor being universal between them all. And it would break if some new structure turns up that modifies how that, either the summing of the color charges or the kinematic factor that enters in front. And in fact, that is going to be the main topic of my talk next week, is that both the kinematic factor and the summing of the color charges breaks when you do a calculation at 4 order, so 4 loops, because there is a new structure that emerges for some observables. So in conclusion, I hope I've given you a broad picture of what this formula means, and crucially, why it's needed and where it comes from. It's needed because it gives us the factorization of the proton dynamics onto universal functions that are independent of the parton collision, but also it resums the logarithms that are present in our process that are needed to make perturbation theory meaningful. And fixing this mu f is how we do that resummation. As I said on the previous slide, next week I will discuss how this can all actually break down in the end when you go to 4th order in alpha S for some observables. So thank you.
Wonderful. Thank you so much for this very nice introduction to collinear factorization. Questions online or in the room? Yeah.
Maybe I missed it, but what was the origin of why the red gluons emitted sort of early in the process were contributing as double logs as opposed to anything else?
Well, it's these red ones are attached to final state particles. So I didn't say this really explicitly, but I gave this calculation of how you got a double log in E plus E minus, where all the radiation was off the final state. And these red gluons are both attached to the initial and the final.
Okay, yes.
And really what this is, what at the core is the red gluon now has actually the ability to go singular in 2 directions. It could be collinear to one of the final state directions or collinear to one of the initial state directions.
Right.
And the collinear to the initial state direction singularity is going to be protected the same way it was in Dirichlet evolution. But it can go singular also when it goes in the direction of one of the final state jets it's attached to. And that singularity isn't protected. That will make a double log.
Okay, thank you.
Other questions?
We have a question on Zoom.
Yeah, Ben, please go ahead.
Yeah, thanks for the talk, Jack. So it seems like this factorization theorem is somehow a subtle mathematical trick of rearranging the way you think about where the emissions are coming from in the process that you're studying. So is there some physical picture or some way of thinking about how this happens physically as opposed to mathematically? Why can we expect these emissions to come from different points in the process?
Yeah, so physically, that's going back to what the pictures I drew at the start, that these are we're trying to pull off the emissions that are intrinsically from the initial state and have low transverse momentum. So if we think of it in momentum space, that's modes in the quantum fields which have wavelengths of order the scale of the whole proton, perhaps. Like they're long wavelength modes. Now, when we probe a high energy partonic cross-section process, what we're probing is really short distances inside the proton because we're probing very high energies. And these really short distances, we don't expect to be sensitive to seeing the overall structure of these long wavelengths that are mixed across the dynamics of the proton. We expect it to see only the short wavelength physics associated with the partons inside the proton, so the quarks or the gluons. So that's kind of the most physical picture I think you can see for it.
Okay, thanks. That's nice. Thank you.
Perhaps a silly or very out there question. When I think of the factorization scale, the mu f, and we talk about it as being something that's separating the parton physics from the proton physics, I would think that it's not just some number that everything lies on one side or the other. You would want it to be very far away from that number. So is there ideas where that's sometimes a range, or is it always just some number that separates?
Yeah, so in practice, I didn't really focus on this, but really what this mu f is it plays a role like a renormalization scale. If you're doing scatter and effective field theory, it actually is a renormalization scale. And the basic logic is that you have your observable has put a constraint on the phase space such that you can't measure more than a given amount of transverse momentum from that initial state. And so you're going to set mu f to being what that constraint is. But this is in order to achieve logarithmic resummation. So order 1 quantities we don't have control over. So you can vary mu f up or down by a factor of 2, and it will still get you the same resummation. At least at leading log accuracy. If you go beyond that, you then need to be more careful. But beyond that, I would really stress I've given a very sort of physical picture that actually doesn't work beyond leading log accuracy. You need to properly think about this as really what's going on. Is the full factorization theorem has definitions in terms of matrix elements for the partonic cross-section and definitions in terms of matrix elements for the parton distribution functions. And both of those matrix elements are singular because of the collinear radiation that I showed you the calculation of at one loop in terms of fitting functions. And the singularity between each matrix element cancels.
Yeah.
So what you can do is you can renormalize the matrix elements, introducing the scale dependence mu f. And then do the evolution in the renormalization scale, which gives you the Diglab equations that I derive.
Yeah. Okay.
And in doing so, you therefore, what the end goal is to do renormalization group improved perturbation theory, where you would then set mu f to a scale which minimizes the logarithms in your partonic hard process. And those logs are determined by your observable.
Okay, all right, thank you very much.
And that would be the way you would see everything emerging if you did a proper Sket derivation.
But that only works if you can assume that this factorizes, right? If you break that, the toolbox is gone.
Yeah, and then
Yeah, exactly. So you can only do it if the factorization does indeed hold. And an alternative perspective on what I'm going to show next week, where I'm going to do everything from sort of fixed order QCD calculations to show that the factorization stops holding at for loops. In Sket, what you find is there is an additional pole in the partonic matrix element, which, there's an additional pole in the partonic matrix element that doesn't cancel with the hadronic matrix element if you take mu f to being too large. And that's the breakdown of factorization that I'll talk about next week.
okay.
Very good. Any last questions? If not, let's thank our speaker one more time. Yeah, thank you so much. Really appreciate this. Have a great weekend, and we'll see you next week.
Yes, thank you very much.